Hi, everybody. Let's go over the types of problems I will want you to know for your first exam. And you'll see here on your practice exam, I just went ahead and labeled it exam one. That's mainly because the practice that I'm going over with you here, it was an exam in my class at some point. Now I'm just using it as a practice. Your exam, problem by problem, will be very, very similar to this. No problem will be the same, but all will be the exact same types of concepts. So please do keep in mind on each of the problems, I want you to show as much as work as possible. And it is quite possible that you could have a correct answer and not receive any credit because of not having the correct supporting work. So please make sure you take that into consideration and show as much work as you can in the space provided on the test. So this first problem, on this exam and on your exam, it will be an absolute value inequality. So I have the absolute value of 4x minus 5 is strictly greater than 11. I'm supposed to remember that if an absolute value is greater than a number, it means if that number is positive, clearly it has to be greater than the number on the other side. If that number is negative, it has to be less than the negative version of the number on the other side. So every time you can just make this a three-part inequality and say the part inside the absolute value is greater than the other side or less than the negative of the other side. And then in order to solve out the three-part inequality, first step here is I would add 5 to each side. When I add 5 to the middle, of course, I get 4x. Add 5 to 11, I get 16. Add 5 to negative 11, I get negative 6. Now I have 4x is between negative 6 and 16. If I divide by 4 on each side, negative 6 over 4 reduces down to negative 3 over 2. 16 over 4 reduces down to 4. So now this is telling me that x is strictly greater than 4 and x is less than negative 3 over 2. It might help you to draw a number line. You don't have to, but if it helps, that's a good thing. We know this one is telling me x is greater than 4, so it can't be 4, but it could be a number greater than 4. And now be careful with this other side. This is telling me that x is strictly less than negative 3 over 2, meaning it can't be negative 3 over 2, but it could be numbers less than negative 3 over 2. So I will want the final answer in interval notation. Please notice I say put answer in interval notation. I want to see this for the final answer. So x is equal to, well, your number line tells you it can go all the way back to negative infinity up to negative 3 over 2. And remember, when you don't want to include a point, you have to put it in a parenthesis. If this had had equal signs here, I would have had brackets around my points, negative 3 over 2 and 4. Since it was strictly greater than and strictly less than, we have parentheses. So final answer, negative infinity to negative 3 over 2, union 4 to infinity. Okay, next problem, completing the square. And this is one of those that if you find the maximum minimum value without showing me the completing the square, I wouldn't give you credit because I need to see completing the square. That's going to be a critical technique that you just have to know in calculus too. You won't be able to work several of the integral problems unless you could put them in the quadratic, or sorry, not quadratic form, but the vertex form of the parabola that's only obtainable by the completing the square method. So I gave you a problem here, 3x squared plus 28x plus 13. We're supposed to complete the square. Okay. First thing I need to do is factor the 3 out of the terms of x. I know that there's no way it can be a perfect square trinomial as long as that leading coefficient is 3. So that's the first thing I did. Now, I underlined this part because that's what I have to input in. So think of this to begin with, nothing there. All I've done is I factored the 3 out of these terms. 3 out of 3x squared gives me x squared. Divide 3 into 28x, you'll be left with 28 over 3x. I went ahead and I separated the 13 right here to the outside. Now I had to think, okay, I need to create a perfect square trinomial. So that part that I underlined there, that's what I figured out down here. Every single solitary time, the term you need in order to complete the square here is always, always half of the coefficient of x. So you say, well, 28 over 3 divided by 2. That gives me 14 over 3. I square that. 14 squared is 196, 3 squared is 9. So I knew in order to have a perfect square trinomial, that constant term c had to be 196 over 9. So I put plus 196 over 9. Now, in order to make up for that, though, we can't just go around adding something to a side of an equation. Now, sometimes you might think, well, whatever you add to the right, why don't you add to the left? Because I need to leave the left y equals. So instead of adding something to both sides, I went ahead and added it to the right-hand side and I subtracted it. But now be careful, you're not just adding 196 over 9, you're adding 196 over 9 times 3. That's why you see on the outside of the parentheses minus 196 over 9 times 3. So whatever I do, I must undo. Now, the reason I did this on the inside was to make that a perfect square trinomial. So x squared plus 28 over 3x plus 196 over 9 factors down to make the binomial squared x plus 14 over 3 quantity squared. Now, if you have any doubt about where this binomial comes from, and it's always, always just the square root of the first term plus half of b in the binomial form. But if you had any doubt, you could take x plus 14 over 3 times x plus 14 over 3. It'll give you that trinomial back. So the superior format of 3 times this trinomial is 3 times this binomial squared. And then on the outside, I had plus 13 minus 196 over 9 times 3. You can easily combine that on your calculator if you need to. We'd have 13 and then minus 196 over 9 times 3. And instead of the ugly fraction, I hit math, enter, enter to make that fraction into a nice decimal. And there, that'll be a little bit crisper screen. So we have the negative 157 over 3. That's where that term right there came from. Now, in this format, and really the main thing I'm looking for is that completing the square format. I want to see that. Now, in order to answer the question, we knew that this was a positive parabola. Every single positive parabola is shaped like a U, so it has a minimum and no maximum. So it's going to have a minimum value where this vertex is shifted. I know this is just the parabola y equals x squared that's been shifted 14/3 of a unit to the left and down 157 over 3. That comes from your pre-calculus shifting knowledge. This is a horizontal shift to the left, vertical shift down. So the minimum is at negative 14 over 3, negative 157 over 3. All right, final answer there. For the next one, really like this one. I'm asking you to find the inverse of the rational function 2x minus 9 over 5 minus 7x. Okay, so first thing I have to remember is, what does an inverse do? An inverse is going to undo whatever the original function did. So that means if x goes to y in the original function, then y has to go back to x in the inverse function. Okay, now, so it should be no surprise that the first step in finding the inverse is to switch the x and y's, because that's literally what an inverse does. So I'll say, okay, y becomes x, x becomes y. Now I need to solve for the new y value. I can't solve for a new y value as long as it's in the denominator, so I get it out of the denominator. I do that by multiplying 5 minus 7y on both sides. When you multiply by 5 minus 7y on the right, it just cancels the denominator out. Now on the left-hand side, in the next step, I'll distribute the x through that group, and I'll get 5x minus 7xy equals my 2y minus 9. Now, my goal is to solve for y. So I want to get every term that has a y on the same side, every other term on the other side. That's what I do in this step. I have a 5x plus 9 on the left. And then my terms of y, I already had a 2y on the right. And if I move the minus 7xy to the right, it becomes a plus 7xy. And then in order to solve for y, I said, well, okay, why not factor it out? And then I can say, okay, if I factor a y out on the right-hand side, it'll leave me 2 plus 7x. And then I can say, okay, y times the group 2 plus 7x is equal to 5x plus 9. Thus, y is going to equal 5x plus 9 divided by what was multiplying y, the 7x plus 2, or 2 plus 7x, either way. Now, I think that this is my inverse function, but now I ask you to prove that your inverse is correct. What we know about all functions composed with their inverses, again, they undo one another. So whatever the original function does, the inverse will undo, and vice versa. So I can say if I compose the original the inverse inside the original function, they should undo one another and result in a solution of x. So I try that. I'm going to take the answer I got for f inverse right down here and compose it inside the original function, meaning replace x with f inverse of x. So I had 2 times x becomes 2 times f inverse of x minus 9 over 5 minus 7 times f inverse of x. Again, you're just taking the original equation f of x, and wherever there was an x in there, replacing it with what we think the inverse is. Now I need to simplify this, and it should simplify to be x. I have a compound fraction. The best way to simplify a compound fraction is to get rid of the denominators inside the fraction. So if I multiply the numerator and denominator by 7x plus 2, that'll be achieved. When I do that, I'll have 2 times the group 5x plus 9 minus 9 times the group 7x plus 2. In the denominator, it distributes to the first term, and I'll have 5 times the group 7x plus 2 minus 7, and the group 7x plus 2 cancels that denominator, so you're only left with minus 7 times 5x plus 9. Now I distribute throughout the problem. I'll get 2 times 5x is 10x, 2 times 9 is plus 18, minus 63x minus 18. In my denominator, the 5 distributes through to give me 35x plus 10. The minus 7 distributes through to give me minus 35x minus 63. Now, it's not coincidental that a lot of terms cancel here. We knew it had to simplify to be x. Well, please notice in your numerator, the constants cancel. 18 minus 18, gone. 10x minus 63x is negative 53x. In my denominator, 35x minus 35x cancel. 10 minus 63 gives me a negative 53. And then I can say negative 53x divided by negative 53 is x, which is excellent. All right, final answer there. Up next, for number 4 here, it's asking you to consider theta being an angle between 3 pi over 2 and 2 pi. So I went ahead and drew theta as an angle in quadrant 4. And remember, anytime you're drawing theta inside of a quadrant, the angle theta needs to be connected with the x-axis. So I went ahead and drew an arbitrary angle theta in quadrant 4. Now I had to know how to label theta. I was told that the secant of theta was 5 over 4. And so in my head, I was thinking, okay, well, secant's the reciprocal of cosine. Cosine is the ratio of adjacent over hypotenuse. So secant is hypotenuse over adjacent. So the first thing I did whenever I labeled my triangles, I said, well, okay, that's hypotenuse, that's adjacent, 5 and 4. And I know that the diagonal, the hypotenuse, is always positive. This has to be positive because it's moving to the right. But now I knew any vertical change would have to be negative. And I knew, hey, this is a special case triangle. This is a 3, 4, 5 triangle. So I knew that that vertical was 3. But since it's going down, had to be negative 3. You could have also used the Pythagorean theorem and said, well, 4 squared plus b squared is equal to 5 squared. And then that would give you b squared is equal to 9. But now whenever you have that, you've got to be careful, because you get, if b squared equals 9, b could equal the positive or negative square root of 9. And so you'd say, well, I know it's either positive or negative 3. Because of the quadrant, you know that the vertical component had to be negative. Please be careful with that. I could see a lot of people making sign SIGN errors on a problem like this. Now, when I go in, once all the sides are labeled, it becomes easy. You can just say, well, as long as you remember your SOHCAHTOA, sine is opposite over hypotenuse. Opposite theta is -3, hypotenuse is 5. So I get the sine of theta is -3 over 5. The cosine we already knew was the reciprocal of the secant, so 4/5. And then tangent is opposite over adjacent. That's the opposite over the adjacent, -3 over 4. You could have also said the tangent is your sine over cosine and get the same answer, -3 over 4. Once you get sine, you know cosecant is just the reciprocal. We were already given secant, and we know cotangent is the reciprocal of tangent, so it has to be -4/3. Now, keep in mind here, I do need all of the trig functions with an angle set equal to their value. Please don't be sloppy with your notation in a problem like this and say sin is -3 over 5 or CSC is -5/3. Please don't do that. I will count off. I need you to be correct with your notation. The tangent of theta is equal to -3 over 4, not tan is -3 over 4. I need the angle in there. All right, up next, I'm asking you to find both solutions between 0 and 2 pi for the tangent of theta is equal to -2. And I'm asking you to round your answer to 3 decimal places. Okay, so both solutions, 0 to 2 pi for the tangent of theta is -2. Now, I went ahead and graphed out where I knew it would be. And I could say, all right, when is the tangent negative? I know it's not in quadrant 1 because sine and cosine are both positive in quadrant 1, so the tangent is positive. I know it's not in quadrant 3 down here because in quadrant 3, your cosine and sine are both negative, thus the tangent's a negative over a negative, a positive. It's only when the sine and cosine have opposite signs that your tangent is going to be negative. And in this case, if the tangent is -2 and you're in quadrant 4, for example, you'd say, okay, tangent is sine over cosine. It's vertical over horizontal. This is the point in quadrant 2 at which the angle theta is going down twice as much as it's moving to the right. Now, again, remember, angle theta, your reference angle to theta would be right here, and you'd say opposite theta is -2, adjacent to theta is 1. It's going to be approximately right there. For theta 1 in quadrant 2, you could say, well, it's the angle in quadrant 2 that has a ratio of -2. In this case, the vertical component goes up twice as much as the horizontal component moves to the left. So it still gets the sign of -2 because it's opposite over adjacent 2 over -1. Now, in order to find those angles, please keep in mind, in this case, your calculator is not going to give you either of the angles that I want. I want angles between 0 and 2 pi. The calculator is only capable of giving me an answer between -pi/2 and pi/2. Because of the way the tangent function has to be restricted for inverse tangent to exist. So it is extremely important that you understand the calculator answer here. It's not the answer that I want, but I still have to find it in order to get to the answers that I want. Okay, so I want answers between 0 and 2 pi, and I'll say I need to be in radian mode. I'll go inverse tangent and of our -2, and it's giving me -1.107. All right, so that inverse tangent of -2 gave me negative 1.107. That's just saying that we know anytime you have a negative angle, you're rotating clockwise. So it's finding this angle here. Well, I want the angle between 0 and 2 pi. So it's telling me this angle, I want the angle all the way out to that point. So all I have to do to find theta 2, it's the one we find more directly, is just say, well, it's going to be that negative 1.107 plus 2 pi radians to get to that. Or in other words, 2 pi radians minus 1.107 to get the 1.576. So please notice here, if I add 2 pi to that, and I get, oh, that's just adding pi. That's the other value. Let me add pi again. If I add 2 pi to it, I get the 5.176. Now, in order to check that answer, I can easily say the tangent of that angle, this better give me a negative 2, or I've proven myself wrong. Boom, it does. Okay, so that would give me confirmation. Yes, that's an angle between 0 and 2 pi such that the tangent is negative 2. Now, for this one, I knew that the angle theta 2 was the same angle that the calculator was trying to give me, negative 1.107. It was just a coterminal angle where I had to add 2 pi radians to it. The other angle is on the other side of the circle in quadrant 2. So I can say, well, in order to get to the other side of the circle, I know that the line straight across has an angle of pi radians. So I was at negative 1.107. And I needed to have a positive angle between 0 and 2 pi. So I just said, well, I know pi is 3.14. So if I add that to negative 1.107, it's going to give me the positive angle that I need here at theta 1. So you can see I just said, well, it's going to be negative 1.107 plus pi, or in other words, pi minus 1.107 to get to this angle. Now, again, let me get it more exact. If you do your inverse tangent of negative 2, you have that approximate negative 1.107 value. If you add pi radians to that to get to quadrant 2, it's telling you your angle is 2.034. And we know that that's in quadrant 2 because quadrant 2 starts at pi over 2, which is 1.57. So this is a pretty good way into quadrant 2 here. Now, I know that if I take the tangent of this answer, I better get a negative 2. Tangent of that answer better be negative 2. It is. All right, so feel pretty good about that problem. Hope that you do too. Please do keep in mind, though, it is certainly not just as simplistic as going to your calculator and expecting it to spit out an answer. It's not. You have to understand how their answer correlates to the problem on hand. It's going to give you a coterminal angle to one of the angles in question. You have to use that information to add 2 pi to it, but then you also have to find your other angle here too. Okay, up next, love this problem. Whenever we're in a Calc 2 class, you might have to integrate something like this. I promise, if you had to integrate that, it would be horrendously difficult in the format that it's in. But if you can write it as an algebraic expression, it's going to be easy to use substitution or some technique of integration to evaluate. So this technique from pre-calculus, extremely important to master. Anytime you have the composition of a trig and an inverse trig function, it's going to be an algebraic function. So in order to determine what that is in this problem, just like we were talking about up here, anytime you have an inverse tangent or any inverse trig function, it's simply an angle. The inverse tangent of negative 2 was a radian angle of negative 1.107 radians, which meant it rotated that direction clockwise. We needed the counterclockwise angle. So the inverse cosine of 3 over x, I don't know what it is because of that variable 3 over x, but what I do know is it's simply an angle. So the first thing I do here is I substitute theta to represent that angle. So I can say, okay, the tangent of the inverse cosine of 3 over x is going to equal the tangent of theta. I have allowed theta to represent the inverse cosine of 3 over x. Since we've done that, we can then say, well, let's find out some information about theta. You could take the cosine of both sides. The cosine and inverse cosine cancel and just give you 3 over x. Now I know that the cosine of theta is 3 over x. Well, what do you know about the cosine function? Cosine tells you that the angle inside of a right triangle, in this case, is going to have the ratio of adjacent over hypotenuse. So I can draw a right trig triangle and say, all right, here's my right triangle. Here's the angle cosine. The side adjacent to theta, sorry, here's my theta. The side adjacent to theta, because the cosine of theta is 3 over x, has to be 3. The hypotenuse has to be x, which means the other leg has to be the square root of the square of the hypotenuse minus the other leg squared. So I get the square root of x squared minus 9. And please don't make the mistake in thinking, well, is that x minus 3? No, it is not. The square root over a sum or difference of squares does not work that way, because x minus 3 times x minus 3 does not equal x squared minus 9. So that's simplest format there. So I can say, well, okay, now that I have my trig triangle set up, can I solve for this problem? Yeah. The tangent of the inverse cosine simplified down to the tangent of theta. Look at your triangle and tell me what the tangent of theta is. The tangent of theta should equal the ratio of opposite over adjacent, square root of x minus 9, all divided by 3. Final answer there, gorgeous. For my next problem, and the last of the pre-calculus problems, I'm asking you to solve an exponential equation. So the first step you should remember is, hey, I need to get my exponential function by itself. The exponential function is 7 to the 3x power. So I try to isolate that. The first step in isolating it is to multiply both sides by 5. I do that. Then I need to get rid of the minus 2, so I add 2 to both sides. Now I need to get rid of the exponential base of 7. And here's where some people would make the horrendous algebraic error and say, well, could you divide by 7? No, because that 7 is not multiplied. That's an exponential base 7. The only inverse of an exponential base 7 is a log base 7. I have to do the inverse of an exponential base 7 by taking log base 7 of both sides of your equation. Now, this left-hand side, when I write it like this, it's literally asking me, hey, what power of 7 is 7 to the 3x? You know, well, it's the 3x power of 7. That's why the log base 7 and exponential base 7 cancel, and I have just a 3x on the left-hand side. On the right-hand side, it's literally asking you, what power would you have to raise 7 to in order to get to a 42? Now, just thinking about, I know the answer is between 1 and 2, but it's going to be an irrational number. 7 to the first is 1, 7 to the second is 49. So the log base 7 of 42, it's a number close to 2. But since it's irrational and I want to keep it exact, I use the change of base formula and say, well, the log base 7 of 42, it is an irrational number. And instead of trying to, since I need an exact value, instead of trying to approximate here, I'll go ahead and just use the change of base formula and say it is equal to the natural log of 42 divided by the natural log of 7. Now, just coincidentally, you went to your calculator and said, well, natural log of 42 divided by natural log of 7, it does give you a number close to 2, and you should say, well, 7 raised to that power better give me 42, or it's not doing what it's supposed to do, but it does. Now, back to here, I need exact and approximate solutions. So this is the change of base formula for that log base 7 of 42. When I solve for x, I would just divide by 3 or put a factor of 3 in the denominator over here. This is my exact form, natural log of 42 divided by 3 natural log of 7. And when I go to my calculator, I'll just say, well, okay, it's the natural log of 42 close divided by the group 3 natural log of 7. And I'll close out my denominator. This should do it. And I get that. I said to 3 decimal places. So to 3 decimal places, it'd be 0.640, which you can just put as 0.64. Okay, now for the next problem. Here's the one where I'm wanting you to estimate an instantaneous rate of change based upon given average rates of change. For this function, I gave you 1 over x plus 2. And we are asked to find the average rate of change from 2 to 2.1 to 2 to 2.01 and 2 to 2.001. So we're going to find the average rate of change over 1/10 of a unit, 1/100th of a unit, and 1,000th of a unit. And as we find that average rate of change over an increasingly smaller interval, we should see a pattern emerge and be able to guess what happens at 2. So first up, the average rate of change from 2 to 2.1. All you're doing here when you say, well, it's just f of 2.1 minus f of 2 divided by 2.1 minus 2. F of 2.1 is just 2.1 plugged into your function. That's where I got this 1 over 2.1 plus 2 minus 1 over f of 2, which is just 1/4. Now, when I did this on the calculator, you can see the answer I got there. I'll go ahead and show that here. If I do 1 over the group 2.1 plus 2, we already know, I was thinking ahead that denominator would be 4.1. So I need to make sure I don't make careless mistakes. I get the 0.243 minus 1/4. But then we're dividing that by 1/10 of a unit. So if I say that divided by 1/10 of a unit, you can see I'm getting the negative 0.060975. Okay, now when I try to evaluate that over 1/100th of a unit, then that first term is really the only term that's changing here. I would get 1 divided by, instead of 4.1, it becomes 1 divided by 4.01. And I'm getting that decimal minus 1/4 for my numerator. That is divided by a denominator of 0.01. When I do that, I get this value of negative 0.0623441397. Now, as I try to figure out what has changed from here to here, I said, well, not a whole lot has changed. It's decreasing from negative 0.0609 to negative 0.0623. So I'm thinking it's went down approximately 0.0014 units. Now, in looking for patterns, I bet from this to this, it'll decrease another not 0014, but 0.00014. So if I'm looking for patterns, I think that the next number should be negative 0.062 and then 48 there. And notice, yeah, that's the pattern that did occur. Now, when I go to that first term, just to see where this number came from arithmetically, we'll get 1 divided by 4.001. That's being subtracted by 1/4. And then our denominator is only 1,000th of a unit. So you can see I get that negative 0.0624843,789. Now, as you keep on doing this, you can say, okay, from this term to this term, it reduced 0.00014. And then I would expect the next one to reduce 0.00014. And I think, okay, it'd be negative 0.062498. And then it would continually keep on reducing. But each time it reduces less and less. And I can say, well, it's looking like this is approaching negative 0.0625 or negative 1/16. Now, if you didn't happen to see that, if you're like, well, how do I see that it's approaching negative 0.0625? One way to get your calculator to help you out with this is you could go in here and say, well, 1 divided by the group x plus 2 on the calculator. And I want to see this where x is 2. I'll just hit zoom 6. This is not a fantastic graph, but it's good enough. Now, what we're looking for is the instantaneous rate of change when x is 2. So I'll go in and say, I want to find, second calculate, instantaneous rate of change. That's the infinitesimally small change in y over the infinitesimally small change in x, dy dx on the calculator. Second calc 6. Tell it where you want the instantaneous rate of change. I want it at 2. I think it's going to be very, very close to these values, or this one right here is my guessed value. Negative 0.0625, gorgeousness. Now, that is the value that it's approaching. Now, if you were working this problem, and let's say you guessed negative 0.06249, I'd be okay with that. I would not be okay if you guessed this exact value right here, because that is an average rate of change, not an instantaneous rate of change. You know, the instantaneous rate of change is going to continually get a little bit less than this. Now, did you exactly know it might be this? Well, maybe not. So I'm not saying you'd have to put that, but you'd have to put a value lower than this. Like I said, something like negative 0.06249 would be fine. But even better yet, the correct answer here, negative 0.0625. Okay, up next, I'll give you a problem asking you to graph out a function given limit attributes. Keep in mind, I say it has to be a function. If your graph does not pass the vertical line test after it's drawn, then it wouldn't get much credit. Has to satisfy the criteria for a function and satisfy the criteria of these limits. So in this problem, I said that you need the limit as x approaches negative infinity of your function to be 5. So I said, okay, all that means is as I'm moving off to the left, I should have a horizontal asymptote going to y equals 5. Done. As x approaches negative infinity, the y value goes to 5. Now, as I move towards the right, as x goes towards negative 3, and this is not just a left-sided limits, from the left and the right, the y value goes to infinity. So you can see, yep, okay, as I move all the way to the left, the y value goes to 5. But as x approaches negative 3, the y values have to go to infinity. The only way I can show that as x approaches a finite value that the y values approach infinity or negative infinity is to draw a vertical asymptote at that x value. So vertical asymptote at x equals negative 3. As I approach negative 3 from the left or the right, the y values had to go to infinity. Now, this is telling me as x approaches 4 from the left, the y values have to go to negative 2. Okay, so I went ahead and said, well, that means I'll have a point on my graph of positive 4, negative 2. It could be an open circle. It could be a filled in dot. It doesn't say whether it exists or not. It's just that's where the limit's going to. So I went ahead and drew an open circle down here at the ordered pair 4, negative 2. As I approach 4 from the right, the y value goes to 7. So I went ahead and drew in a point up here at 4, 7. Now, I had to connect the part, the limit as x approaches negative 3 from either direction had to go to positive infinity. So I had to take this as approaching negative 3 from the right goes to positive infinity, with this approaching 4 from the left equaling negative 2. So once I do that, then all 3 of these are achieved. Then I can say, yeah, but as I approach 4 on the right-hand side, I have to go up to 7. That's where this came from. Now, how did I know I wasn't coming from down to that value? Well, because I know as x keeps on going to infinity, the y value has to go to negative infinity. So I can say, okay, I can achieve the limit as x approaches 4 from the right is 7, and the limit as x approaches infinity is negative infinity with that portion of the graph right here. But now please keep in mind, you can't continue that on over here because then it would not be a function. And also you would not have the limit as x approaches 4 from the left being -2 if you try to connect it up here. So has to look something very similar to what I have here. Now, the only thing that you could do is you could say, well, could I fill in a dot here? Yeah. Could I fill in a dot here? Absolutely. Could I do both? No, because then it's not a function. I didn't say where f of 4 existed. And in this case, it's probably safer just to leave an open circle at both points. For the next problem here. Next problem is the easiest problem on the test, where this is a problem out of section 2.3, where if we have a curve, the portion of the curve where the limit exists, if it's a nice smooth curve, then the limiting value is equal to the function's value at that point. We know the vertical asymptote of this function would be at -7, but x equal 2, it's going to be perfectly continuous there. So if I ask you to evaluate the limit as x approaches 2 of even this rational function, you say, just plug it in. You'll get 5 times 2 minus 2 over 2 plus 7. Gives me 10 minus 2 for 8 over 2 plus 7, 9. 8 over 9, that answer would be fine. The next one, I will give you 2 continuous functions inside of a piecewise function and ask you to make the piecewise function continuous. So in this problem, it's important that you understand, okay, the only value where this could possibly be discontinuous is at the point where these two are supposed to link up. What if, as they're approaching C, one side's down here and one side's up here? Well, then there's going to be a discontinuity. I need to make sure the limit from the left, in this case, as x approaches -3, is equal to the limit from the right as x approaches -3 from this or on this function f of x. So as I approach 3 from the left, and here's where students will get confused. They'll think, well, you can't plug a 3 in from the left because x has to strictly be less than 3. You still need to know the open circle that it's approaching so that you can make the left-hand limit equal to the right-hand limit. So I literally have to plug 3 into the first function and 3 into the second function to get the limit from the left and the limit from the right. When I plug a 3 into the top function, I get 3 squared minus c. When I plug a 3 in for x in the bottom function, I get 4 times 3 plus 3c. So this gives me 9 minus c is equal to 12 plus 3c. If I get my c's on the same side, 4c on the right, constants on the other, subtract 12 and you'll get -3 on the left. So I can say this piecewise function is going to be continuous if and only if 4c is equal to -3, thus c has to equal -3 over 4. Final answer. Now for the next set of problems, these are the ones where we have algebraic limits. This would be like the problems in section 2.5. The first problem I'm giving you here has a polynomial, well, a quadratic over a quadratic. And what you know in these is that it should be of indeterminate form, which means when you try to plug in the value, you're going to get a 0 in the numerator and a 0 in the denominator. The function does not exist at the value where I'm trying to have you take the limit, but we know that that doesn't mean that the limit does not exist. Most cases, the limit does exist. And if the limit exists, then there will be an algebraic solution that enables you to plug in the value. Okay, so in this problem, as soon as I see it has a limit as x approaches 3, I knew that my numerator and denominator had a factor of x minus 3. That's the first thing I did. Please remember to rewrite your limit notation until you can physically plug a 3 in for x. I can't do that right now because I would be dividing by 0. So I leave the limit as x approaches 3. My numerator, x minus 3, and then -3 times what is +3. So I said, well, -1. That's where the x minus 1 came from. I knew the denominator had a factor of x minus 3 as well. The other factor, I just determined -3 times what is -12. And I said, well, that's going to be a +4. And I know 4 plus -3 will combine to give me my plus x in the middle. So factored out both the numerator and denominator. Now cancel out the factor causing the trouble. And this will just become the limit as x approaches 3 of x minus 1 over x plus 4. You plug in the 3, and in your numerator, please notice from this step to this step is the first time I've been able to drop that limit as x approaches 3. Here it's still needed, here it's not, because I physically plugged a 3 in for x. I get 3 minus 1 over 3 plus 4. I'll get 2/7 for my final answer. For the next algebraic limit problem, we have the limit as x approaches 16 of x minus 16 over the root of x minus 4. What I would like you to see is that numerator is a difference of 2 squares. It's going to factor to be the square root of x plus 4 and the square root of x minus 4. So as soon as I see that, I can see, well, the square root of x minus 4 cancels with the denominator. That just leaves me the limit as x approaches 16 of the square root of x plus 4. Can I plug a 16 into that? Sure. Now that I got rid of that factor in the denominator that was causing the trouble, you most certainly can plug the 16 in. You'll get the square root of 16 is 4. 4 plus 4 is 8. Please notice that that limit as x approaches 16 stayed in until I physically plugged a 16 into the square root function there. Square root of 16 gave me the 4. At this point, I could stop putting the limit as x approaches 16. Final answer. In my next problem, this is the one that I will give you where the denominator is not easily factorable. So whenever you're thinking about this one, please don't try to go back to your pre-calculus techniques and say, hey, it's a 4-term polynomial. I'll be able to factor it using factoring by grouping. I can group the first 2, group the second 2. That rarely ever works. So no factoring techniques work other than, again, use the logic of the limit to help you factor it. Just like back in problem 12, where I had the limit as x approaches 3, and I said, well, we know x minus 3 has to be a factor in the numerator and denominator. Again, we know that. Limit as x approaches 3 tells me that my numerator has a factor of x minus 3. And then it's very easy to find the other factor. The other factor, I can say, well, -3 times what is -21? And I say, well, -3 times a +7 is -21. 7x minus 3x will combine for plus 4x in the middle. So I know my numerator factors pretty easily. My denominator, I promise you, also has a factor of x minus 3, but it's not so easy to get the other factor. I had to use long division. So I say x minus 3 divided into that denominator so that I can write it into factored form. I went ahead and did, well, x divides into x cubed, x squared times. X squared times x is x cubed. X squared times -3 minus 3x squared. We subtract those terms out. The x cubes cancel. Your next term would be minus 5x squared plus 3x squared. That's giving me a minus 2x squared. Then I just bring down my next 2 terms. Now you'd say x goes into -2x squared, -2x times. -2x times x is -2x squared. -2x times -3 is plus 6x. Again, you always subtract out those terms. That's how the -2x squared terms cancel. I'll have 13x minus 6x for 7x. I bring down the minus 21. Last time I say, okay, x will go into 7x 7 times. 7 times x is 7x. 7 times -3 is -21. And then we knew that these had to cancel. It had to be a factor. So no surprise, we get a remainder of 0 when we subtract out the 7x minus 21. That's just confirmation. Yes, our terms are exact factors. Our denominator factors into x minus 3 times x squared minus 2x plus 7. Now that enables me to do like we did back in problem 12, where we say, okay, cancel out the factors of x minus 3 and just write this as the limit as x approaches 3 of x plus 7 over x squared minus 2x plus 7. At that point, you can plug the 3 in. When you do in your numerator, it's going to simplify to 10. In your denominator, you're going to have 9 minus 6 plus 7, again 10. And you can say, well, all right, 10 over 10, final answer of 1. Good problem there. The last of the algebraic limits, I'm wanting you to look at the limit as x approaches 2 of x to the 4th minus 16 over x cubed minus 8. So I went ahead and rewrote this as the limit as x approaches 2. Your numerator is a difference of 2 squares. You'd say, well, x squared plus 4 times x squared minus 4. But then remember, x squared minus 4 further factors to x plus 2 times x minus 2. So that's my fully factored final form of the numerator using difference of squares formula twice. In my denominator, it's a difference of cubes formula. I want you to think of this as x cubed minus 2 cubed. X cubed minus 2 cubed factors to be x minus 2 times the group, the square of the first term, x squared, plus the two terms multiplied by each other, 2x, plus the square of the second term, plus 2 squared is 4. That's your difference of cubes factoring formula. You do need to know for this problem, difference and sum of cubes factorization problems. I guarantee you I'll either put a numerator or denominator that requires either difference of cubes or sum of cubes in order to factor. So once I factor this problem out, I can say, well, the factor causing the trouble is the x minus 2. Not surprisingly, that factor causing trouble can be canceled in the numerator and denominator, leaving me the limit as x approaches 2 of x squared plus 4 times x plus 2 over our trinomial remaining in the denominator. At that point, you're guaranteed you can go ahead and just plug a 2 in. So from this step to this step, we drop the limit notation, plug the 2 in for x. When you do, that first factor is going to be 4 plus 4 for 8, second factor 2 plus 2 for 4. Your denominator, all of the terms are 4, 4 plus 4 plus 4. So I would get 32 over 12, which is going to reduce down to 8 over 3. Final answer. Now for the last two problems. Section 2.6 had squeeze theorem, and where we have sines and cosines most notably in there. If you have x approaching 0, yet inside the sine or cosine function, you say, well, yeah, but as x approaches 0, that sine or cosine function, the angle does not exist. So what's the cosine of an undefined angle? And you say, well, the limit, it doesn't matter that it doesn't exist at the point. It only matters what happens as we near the point. And what we know is that that sine or cosine will exist as we near 0. And wherever it does exist, it's always between -1 and 1. That's going to be the first step in setting up the squeeze theorem in these problems. So the cosine of e to the 1 over 0 power as x approaches 0, yeah, that's undefined. However, as we approach 0, it is defined. So we can say, well, all right, the cosine of this angle e to the 1 over x, wherever it is defined, it is guaranteed to be between -1 and 1. That needs to be the first step. The cosine is between -1 and 1. Use that information to set up your small function and your large function. Your small function is always going to be when you replace the cosine with the smallest it can be. So I can say, well, it's x cubed times -1 forms my small function, and we're guaranteed that that's going to be less than or equal to x cubed times the cosine of our angle e to the 1 over x, which is in turn less than or equal to x cubed times the largest the cosine could ever be, which is 1. Now, show that since we know our functions between these two, that it doesn't matter whether it's the small function or the large function, they have the same limit as x approaches 0. That's what I do in this next step. The limit as x approaches 0 of my small function, x cubed times -1, it's the exact same as the limit as x approaches 0 of my large function, x cubed times +1. So you'd say, well, as x goes to 0, x cubed is 0, and that's going to be multiplied by either a negative or a +1. I said, it doesn't matter if you multiply 0 by a positive or a -1, you get a 0. That is the logic of the squeeze theorem. Now we say, well, the large function and small function both go to 0, so that is conclusive evidence that our function in the middle must also go to 0. So we say, therefore, the limit as x approaches 0 of x cubed times the cosine of e to the 1 over x equals 0. Quod erat demonstratum. Now, for the last problem here, in this one, I gave a one-sided limit, and I'll try to make sure it shows up very well. It didn't show up too well on this printed out page. This should be the limit as x approaches 5 from the right of the fraction 7x minus 4 over x squared times x minus 5. So in this problem, anytime you're trying to evaluate a one-sided limit, what we're supposed to remember is that, well, wherever we can plug it in, we should plug it in. So in the numerator, I just go ahead and plug the 5 in, 7 times 5 minus 4. In my denominator, the first factor, x squared, I can plug a 5 in there, 5 squared. It's the second factor that would become 0 if I just plugged in a 5. So I'm thinking, okay, it's really the limit of a number approaching 5 from the right. So in my head, I need to think of that as 5.1 billion zeros and a 1. So some number getting incrementally close to 5. Can I help you out? Yeah, hold on just a second.